Okay, so yeah, I've been asked to talk about Berry phases, and there are many ways of doing it, so I thought a little bit about it. So as you know, Berry phases occupy a sort of a special place in quantum mechanics, also in the history of quantum mechanics, because it's in a sense the one fundamental fact about non-relativistic quantum mechanics that was missed by the founding fathers, let's say, in the 20s and 30s. And people started seeing some funny things in the 50s, 60s, Aronoff bomb effect, and they were, like in the Feynman lecture, they are presented still in a sort of mysterious way. And eventually, Michael Berry sort of put it all together and made it an integral part of quantum mechanics, and now it's explained in textbooks. So from this history, you can sort of see that it's subtle. Otherwise, all those smart people would have understood it from the very beginning. But at the same level, it's also very basic. But now coming to our topic, which is topological materials, there is another difficulty, which is that all these Berry phases are defined in abstract spaces, like reciprocal space or some parameter space. And of course, we live in real space, so there is an inherent difficulty about that. But on the other hand, when you start thinking what are the observables that in our field come up from geometric phases, they are typically, basically, electrons moving. So it's eminently a real space picture, or one can guess that there is a real space picture underlying it. So actually, what I'll try to do this morning is, I guess, demystify Berry phases. And the way I'll try to do that is actually by spending a lot of time before even mentioning them in the lecture. I think it will be a good 1.5 hours before you see the expression for the Berry phase. And instead, I'll focus on a real space picture. So that's the first point. The second point is that I'll spend the whole lecture talking about a single problem, which is electric polarization. So there are several advantages to doing this. The first one is that you can talk about this problem in one dimension. It's an eminently one-dimensional problem. Of course, real materials are three-dimensional, but then the polarization is a vector with three components, and you can treat one of them at a time. But for pedagogical purposes, you can just think of a one-dimensional system, and then the polarization is just a scalar, and that's what I will do for the entire lecture. The second advantage is that so polarization is a property of insulators, and you only need a single band. So I'll be working for the entire lecture with one dimension and a single valence band, okay? So it's very simple. So that's good, I think, for introducing concepts. But what is amazing is that although it's so simple, it's extremely rich. So by studying carefully this problem, we'll introduce a number of concepts which are really some of the main themes of topological materials. So obviously Berry phases, but also edge states, and these sort of intriguing bulk boundary correspondence. I'll talk a lot about something called Wannier functions. And then I think I'll have time to arrive at some other concepts like Chern numbers. And also, as we heard yesterday in the afternoon lecture, a one-dimensional problem like the one I'll discuss is the simplest example that gives rise to a topological classification of phases. So symmetry protected topological phases. Okay, so I hope to cover most of these things during the lecture. But so let me maybe start by setting up the problem. So why is there even a problem, right? We all learn in E&M courses, electricity and magnetism, about polarization. So at some very basic level, polarization is a dipole moment okay, so in one dimension per unit length, right? That's the definition. So dipole moment per length. And I'm talking about a 1D system, which I will call a chain. So this is the polarization of our chain. Okay. So this is okay for a finite system that has a boundary, and it has some length L. But what about the periodic system? So we like to do calculations under periodic boundary conditions. That's very convenient. So the question is, can we define this material property as a bulk property that is independent of the surface termination? Or, in other words, if we get rid of the surface altogether by going to periodic boundary conditions, can we still define the polarization? Okay? So that's sort of the theme that will underlie the entire lecture. So some of the old textbooks propose, so I will call that the bulk polarization to distinguish it from the polarization of a finite chain. Okay? So now we have our lattice with some lattice constant A. And some old textbooks propose the following definition, which is the bulk polarization is the dipole moment per unit cell. So we divide by the cell length, and we integrate the charge density over a cell. So by the way, I forgot to write down the first formula that I want to keep there, which is just an explicit version of this definition, where the polarization of the chain is just the first moment of the charge distribution, which has an ionic part and an electronic part, divided by the length of the chain. And so the proposed bulk definition would be something just like that, but now you have a periodic charge distribution over an infinite chain, and you just integrate over one period. So from some point x0 to a point x0 plus a lattice constant, the periodic charge distribution. Okay? Yes? Oh, yes. Right. Too many x's around. Thank you. Okay, so that sort of works in some cases. Let me draw a cartoon picture here. This is our system. And now I want to think of it as a sequence of polarizable units which are disconnected. So what I mean here, so I have positive ion charges, but then this circle just denotes the region where the electrons are spread out. Okay? And then the idea is that these minus represent where the center of this charge distribution is inside each unit. And then you can apply this definition simply by choosing your initial point x0 in a region like this. Okay? So that will give you a polarization vector pointing like this. Okay? So in this case, as I said, the charge distribution is a sum of point charges due to the ions this is our rho ion that is over there. And then there is an electronic part, which is not a sum of delta functions because electrons are smeared out, but it's some periodic function of x. Okay. So everything looks fine, but you can already see that you may run into problems because at some level where we decide to place this cut is totally arbitrary. Any length of A is allowed, so nothing prevents me from choosing this other unit cell. And then what is the polarization? So it's points from the negative to the positive charge inside the cell, so it now points like this, right? So which is correct? Well, intuitively, this choice seems more natural, right, than this one. And why is that? Because we're placing the cut in a region where there is no charge density. So that sounds like a good empirical rule. Define the polarization from this formula, provided that you choose your cell in such a way that the boundaries are regions where the charge density is negligible. And okay, that's okay maybe for a molecular crystal composed of polarizable units which are weakly bound, so the charge density drops to 0 between them. But real solids are not like this, right? Most of them. So if you look at the charge density of a solid, it's going to look more like, you have something like this, where the peaks are the locations of the positive charges, but then you have the electrons basically smeared out everywhere. So obviously we have a problem because there is no natural choice of cell to make under these conditions. Wherever you place your x0, you're going to hit some charge density. And then what that means is that as you move your cell, as you move your x0, you can get, the value that you calculate changes continuously. And actually, if you average over all x0s, you get 0. So it's pretty ill-defined. Okay, so that's sort of the problem. So this approach, this proposal that you can find in all textbooks, it's really not a good way to arrive at a proper bulk definition that is valid in general. So let's try a different approach, which is very physical, which is almost by definition, the bulk limit is called the thermodynamic limit, which is you take a finite system and you make it very large. So, proposal number 2, so if this was proposal number 1 that we crossed out, proposal number 2 would be, let's try to define the bulk polarization as the limit of L going to infinity of the polarization of a finite chain. Okay? So that also sounds very plausible, but let's look at the units of polarization. So in one dimension, polarization is a dipole per length. So a dipole is a charge times a distance. And then we divide by length, right? So in 1D, polarization has units of charge. So what that means is that we have reasons to worry, because we have no guarantee that spurious charges at the ends of a very long chain will their contribution may not go away in the thermodynamic limit. Okay, because those charges have the same units as the quantity you're calculating. Okay, so in other words, this limit may be ill-defined because it may depend on the details of what's happening at the ends of a very long chain. Okay? To make this point, to drive this point home more clearly, let me propose a sort of a thought experiment. So let's take our chain, maybe a chain with two different sides, something like this. Let me call E1 the on-site energy. So we have alternating sites with two different on-site energies, E1, E2. And we have some long chain. And let's say this is the last atom of our chain. But now suppose that I do some modification to the way I've prepared my sample such that I raise the energy of this last point. So intuitively, we might think that by raising the energy at this point, the electrons don't want to stay there, so they may get pushed away from this point to the other end of the chain. Okay. So if that is the case, then the change in the polarization of the chain due to this modification at the edge, which is going to be basically the change in the surface charge at that edge, it's going to be it's going to be non-zero. So, but then obviously the polarization is not about property because it depends on how what's going on at the surface. So I'll sometimes use the word surface, which is appropriate for a three-dimensional system, but of course here surface really just means the end of the chain. Okay? So if this is the case, so if by playing with the on-site energy at the end of the chain you can push continuously charge away from it to the other end, then it's hopeless. Polarization is not about property. Actually, this topic was very hotly debated in the 60s and 70s when people were trying to understand whether certain properties related to the polarization, like the piezoelectricity, which is the change in polarization as you strain a crystal, is about property. So there were very heated debates about this topic in the 60s and 70s, because indeed, this limit is subtle. So it's not clear that boundary contributions or surface charges can be argued away. Okay? So at some level, the reason why the thermodynamic limit is tricky, now coming back to this kind of picture, is that the electrons are all over the place. So they extend over the entire sample and they don't fall to zero anywhere in between. Okay? Of course, I should say that that is true in one dimension without disorder, as you may know. If there is, that's a problem. If there is disorder, then states get localized, but we'll not worry about those things. Yeah. Oh, okay, yes. Yeah, I think I was not very clear. So you remember from your E&M courses that the presence of a polarization manifests itself on the surface as a bound surface charge, right? So this is from you, right? So in one dimension, the one-dimension version of this formula is just P equals the charge at the surface. Okay? So if you're able to change continuously the charge at the surface by playing with the surface preparation, that means you're changing the polarization. But then the polarization is sensitive to the surface, so it's not about property, which by definition is a property which is not sensitive to the surface. Okay. Okay, so I was saying that at some level, all the difficulty has to do with the fact that unlike ions, which are perfectly localized, electrons are extended, right? So if you solve for the eigenstates of a chain, so now we're starting to get to quantum mechanics. Then you can write the electronic charge density. So some of these states are going to be occupied, some are going to be empty. And to get the charge density, you just take the occupied ones, and then you take the, so it's this, right? Excuse me? Sum over occupied states. So of course, here everything is done at the single particle level. And so it's the number density times the charge of the electron, okay? So, and now I want to make a very simple observation, which is, so this is extended. So by the word extended, I just mean that it spreads out over the entire chain. Most of the eigenstates, the individual eigenstates, except possibly a few at the edges, are also extended, right? Again, without disorder. And the trivial observation that I want to make is the following. Trivial but important. You can reconstruct the same extended charge density by writing an equation like this, where instead of the energy eigenstates, you use some other states which are localized. Okay? Sorry, I'm not being very good with the colors. Let me try to stick to black for the text. So this is the same quantity that is on the left-hand side of that other equation at the far end. But now I'm building up that object out of localized objects. So the trick, of course, is that individually they are localized, but to reconstruct the extended charge density, they are localized at different places along the chain, right? So nothing mysterious at that level. Another observation is that if this equation takes precisely the same form as that one, that means that the two sets of states, the psi's and the w's, are related by a unitary transformation. Does that sound okay? Okay. It's just a new orbital that I've called W. Yes, so these psi's are defined by this equation, right? Now, I am, for the moment, just introducing some new orbitals, which I will define later. But at this point, let me just write one more equation to see if you agree with it. Whatever these orbitals are, and I've not told you yet what they are, they must be related to the original ones by a unitary matrix. Which means that U dagger U, I'm going to change the pen in a moment. Yeah, I know. I will change the pen. As Francois said, we give a lot of money to whoever makes these things. So they create two problems. You cannot see the board because it's white. And then you have to give them money all the time. So Nothing like century-old technology, which is a blackboard and chalk. So, coming back to your question, even though I didn't tell you what these orbitals are, do you agree that given that equation, if this equation is to hold, they have to be related in this way? So the simple exercise you can do is to plug this expression into there, and then to recover that one, you basically have to use this property. Okay? I'll leave that as an exercise. Okay. And so the advantage is that if we have a localized representation for the electronic charge density, and that's going to be the exercise I will do now, the thermodynamic limit becomes much more manageable. Okay? So that's sort of the logic of what I'm trying to do here. So I've gone from a double problem, which is extended, to a somewhat easier problem, which is extended localized, where I now have something which is closer to the ions, which were not a problem in the textbook definition. Okay? So, of course, your question is the central one, how to define these orbitals W, right? Which is to say, how to choose the unitary matrix. So given an initial set of eigenstates, how to choose this unitary matrix. So if I were to ask you what is the most localized orbital that you can give me, what would you say? Precisely, so a delta function. And now, a delta function is an eigenfunction of what operator? Right. So I'm using this very compact direct notation, which is, in this particular equation, is a bit mystifying because X plays three roles, right? So we have the X operator, we have the X0 eigenvalue, and you have the X0 eigenstate. And then in the position representation, this eigenstate is a delta function, right? Okay. So, if we're given a choice of constructing localized orbitals, that's what we would do. They are infinitely localized. But what I want to do is to construct orbitals. I don't have complete freedom to construct these orbitals. I have to make them up out of the occupied states. Okay? So let me introduce, as an intermediate step, a projection operator. I usually write it P, but I already used the symbol P for polarization, so I'll use this sort of double bar P for the projection operator into the occupied states. And now I'll answer your question. So the size were defined by this equation, right? And now I'm going to define the W's by an equation which is similar to that one, meaning it's also an eigenvalue equation. Okay. So what I have here, I will call the projected position operator. So you have the X operator sandwiched between the projection operator. And that compound operator, PXP, is the operator that is replacing the Hamiltonian in my eigenvalue equation. And so the eigenvalue I call X of J. And I put the superscript WF because I will call these orbitals Wanny functions, okay? And so this eigenvalue has units of length, and it's nothing but the center of this orbital, so the center of mass of this orbital. Okay? Is that clear? So I forgot, I was trying to keep some important equations on the board, so let me catch up. So that's our eigenvalue equation. So what is the reason? Yeah, please.
I have a question about this before.
Yeah.
Is it obvious that you construct localized states from only the occupied orbitals, occupied sites? You have a complete basis, so you're not sure.
Precisely. That was my next sentence. So let's try to motivate this equation. And the way I'll motivate it is by comparing with this one. Okay? So the only difference is that I've sandwiched x between the p's. So in a sense, what this equation is doing is getting the functions that are as close as possible to delta functions, but made out of occupied states. So that's the motivation. So in the limit that you have a complete set of states where the projection operator becomes the identity, then these eigenfunctions become the delta functions. Okay? So does that sound like a reasonable argument? Okay. So that is sort of the original argument for introducing this equation. And however, your question is quite deep, and there is a better answer, which I will not go into details unless I have time at the end, which I doubt, but I will just state it, and I can give you notes or just tell you on the side the proof. You can actually be quantitative about this statement. So you can prove mathematically, it's very simple and very pretty, that these orbitals are the most localized orbitals that you can make out of the occupied states. So to be quantitative, we have to define a measure of localization, right? So a very intuitive measure is the quadratic spread, which is just the second moment of the distribution. Okay. So the claim, which I will not prove, but you can ask me about it, how to do it, is that the orbitals defined by this equation make this quadratic spread as small as possible. And so since these orbitals were a function of the initial ones by a unitary matrix, so what I really mean is that out of all the possible U matrices, the ones that solve this equation are the ones that make this quantity as small as possible. And this is a positive quantity, right? This is a spread, a variance. So, okay. So just to give you a flavor for the proof, it's one of those tricks that happens all the time in this business, which is you use the resolution of the identity. So you insert complete states in the middle. So you write one as projection into occupied states plus empty states, and you start seeing the p's appearing. So that's how it goes. Okay. But let me tell you maybe in practice how we do this in a computer code. I will later show you some results, and this is precisely what we do. So we first solve this equation, and then you construct a matrix, which I will call capital X. So I just construct this Hermitian matrix, which are the matrix elements of X between the eigenstates. And this is done for a finite chain, so everything is well defined. There is no problem with having a non-periodic operator in a periodic system. That's funny, but we're talking about finite systems. Okay, then I diagonalize this matrix to get a new matrix X tilde, and U is the unitary matrix that diagonalizes X. So, and then from that, on the diagonal, so this guy is diagonal, and on the diagonal, what you have is just these center of masses of the various orbitals. So, in a tight binding code, this is a completely trivial procedure, right? So you just have a finite Hamiltonian matrix, you get your column states, you sandwich X between them, and then you diagonalize, and then your eigenvalues are the centers of your orbitals. Okay. So once we've reached this point, things start to look better. Because I can just evaluate equation. So what I want to do is to plug the middle expression for the electronic density in terms of these localized orbitals. So equation 3, the right-hand side, I guess, into equation 1. Okay? And so what I get okay. So X ion J is just the location of one of the ions in your lattice, in your chain. So these are real point charges, right? So these are, we're treating the ions classically. So these are just classical positive charges. And, this is totally quantum mechanical. So the real charge is spread out, but in this representation, what I've done is I've used, I've mapped rigorously the quantum mechanical problems into fictitious point charges for the purpose of evaluating this quantity. So PT just means point charges. Okay? So bear in mind that these orbitals are not infinitely localized, so they are not point charges, but they have a center. And what enters in the expression for the polarization is just the center of those charges, because it's a first moment. Okay? So do you agree that if you plug the right-hand side there into there and you do the integral, you get that equation? Okay. Yes, please. Xj superscript WF is the eigenvalue of this equation, which is to say is the center of mass of the eigenfunction. So, the orbital is localized, is something like this. And it's just this point here. So there are many orbitals. So this is j equals 1, this is j equals 2, and it's just the center. It's sort of the expectation value of the charge distribution of that orbital. But because the orbital is localized, you have a sequence. Is that okay? Okay. So, armed with this equation, we are in a much better position to then take the thermodynamic limit, which is what we set out to do. to see if we can get a bulk expression. Okay? And now I will say something which is, I think, the only point in the argument where I will ask you to sort of take my word for it, but I think it's extremely plausible, which is the following. What I want you to believe is that if you have a very long and very pristine chain, so I have a very, very long, perfectly crystalline chain. So these orbitals are going to be, you have many of them, they are localized on different sites. And those that are in the middle, very far from the end, they just look around and see a perfectly periodic environment, right? So they don't know that they are actually living in a finite chain with some imperfections, something, you know, some details of what happened at the surface. They don't care. Okay, does that sound reasonable? And so such orbitals are going naturally to come in periodic images of one another. If you just have one electron per cell, you're going to have one of these orbitals at some point x, and the next one, the neighbor, is going to be at x plus a lattice constant, and so far. When you start getting close to the boundary, so when the decay length of these orbitals, you know, there is some amplitude at the edge, then they start seeing the surface, and maybe they are no longer perfectly arranged. And so, for example, the spacing is no longer exactly A, and maybe their spread changes, but that only happens close to the boundary. Far from the boundary, these orbitals are all twins, periodic images of one another, sitting, you know, separated by a lattice constant. Does that sound reasonable? So I will use that. It can be proven, by the way. If you want to see the proof, go to your search engine and Google Kivelson and Vanier. I think it's the only paper on Vanier function that Kivelson wrote, 1982, and that's actually where he introduced this projective position operator as a way of constructing Vanier functions. He was interested in soliton problems like Dario is. And so he has actually rigorous proof of this, I think. But anyway, I think it's sufficiently plausible that we can use that fact. So now, let me make a cartoon of this arrangement of classical charges and fictitious point charges sitting at the Vanier centers. Yeah, I'll use color. Okay. Let's see. So, you know, right at the surface, funny things can happen, as I told you. So let's create a defect if you want. So let me put another one here. And the next step in the argument is going to be to divide this long chain into 3 sectors, which I will call head, tail, and bulk. Okay? And this partition of the chain into 3 sectors is highly non-unique. And there are only a few simple rules that we need to keep in mind. So the boundaries between these 3 regions are placed, which is actually not true in this cartoon, sufficiently deep inside the sample in a bulk-like region. Okay, so, you know, I have a small board, but maybe I should have put it here. But where I place the cut, let me call that x0, is in a bulk-like region. So to the right is bulk-like, to the left not so much. From here to there, I have precisely an integer number of unit cells. Okay? So the length of this bulk region contains exactly an integer number of cells, which I will call NB. So that means that this second cut here is at x0 plus NB times the lattice constant A. Right? Finally, I will take L go to infinity, and in that process, it's going to be the bulk that is getting larger and larger and larger, and the head and the tail remain small. So the head and the tail occupy a non-extensive fraction of the length of the chain. So in the thermodynamic limit, L is going to be approximately equal to A and B. Yes? Right, so that's sort of an extreme example of how the periodicity gets disrupted at the surfaces. You can do funny things at the surface, maybe, you know, some charge migrated, was attracted, you know, yeah. At the other end, I have, so I also want to be, I want my chain to be overall neutral, so I've put an extra plus charge here, so I've put an extra minus charge there. Sorry? Yeah, you can. It's just to illustrate how the charge distribution is not periodic at the ends of the chain. You know, another thing I could have done is just to change the distance between the charges without adding any new charges. Just change the distance. That would have been another way. But this is sort of more clear or more extreme. Okay. So once I've done this assignment of my fictitious charges to each of the three regions, then obviously this equation, which is just summing up the contributions from individual point charges, breaks down into three parts, right? So I have P of the chain equals P bulk So let's compute them. So for the bulk, following our rules, let me throw this away. So as I told you, this length here is basically the length of the bulk region, so I can replace L by A and B, making a negligible error in the thermodynamic limit. And now I sum over just the point charges inside the bulk region. Right? But because this region, by construction, is bulk-like, these guys are just periodic images of one another. So, for example, the ions